Hey there, and welcome. Think about the water molecule, H2O. We see it, we drink it, we are it every single day. And it looks so simple, right? Just this little bent molecule. But that bend, that specific shape, holds an incredible chemical secret, one that shapes our entire world. Today, we're going to crack it wide open.
Everything, and I mean everything, comes down to this one super precise number, 104.5 degrees. That's the angle between the two hydrogen atoms in water. Now this isn't some random number. Oh no, it's the result of a fascinating quantum mechanical tug-of-war happening right inside that central oxygen atom. So, that's the big question for today, isn't it? Why 1045? Why not 108 or 95 or just a nice clean 90? Why this exact number? Well, to figure that out, we first have to look at what the simple theory thinks the angle should be, because there's a really interesting disagreement.
Okay, so let's get into it. Your basic chemistry textbook theory, which we'll unpack in a sec, predicts this perfect symmetrical angle of 109.5 degrees. But when we actually go out and measure a real water molecule, we get 104.5. That's a 5-degree difference. And look, that might not sound like a lot, but in the tiny world of molecules, that is a huge deal. So let's solve the case of the missing 5 degrees.
Our investigation is going to start with the standard model. You know, the first layer of the onion, the explanation you get in Chem 101. It all kicks off with a really important idea called hybridization. So, to make enough room for its two hydrogen buddies and two pairs of its own electrons, the oxygen atom kind of remodels its electron orbitals. It takes one of its spherical s orbitals and three of its dumbbell-shaped p orbitals and just blends them all together. The result, four brand new identical hybrid orbitals called sp3 orbitals.
Now, in a perfect world, if these four new orbitals were all exactly the same, they'd want to get as far away from each other as possible. And the way they do that is by arranging themselves into a perfect tetrahedron. This setup creates that magic angle we talked about, 109.5 degrees. But, as we already know, water doesn't follow the rules. Something is messing with that perfect symmetry.
All right, it's time to meet the prime suspects in our little chemical mystery, the two lone pairs of electrons hanging out on that oxygen atom. These guys are the key to the most common explanation for why water is bent the way it is.
So you've got these four groups of electrons around the oxygen. Two of them are busy. They're tied up in bonds with the two hydrogen atoms. But the other two, the ones we've highlighted here, they aren't bonded to anything. They're the lone pairs. And these lone pairs are, well, they're a little pushy. They like their personal space.
So the textbook explanation goes like this. Because these lone pairs aren't stretched out between two atoms, they're a bit more concentrated. They're puffier. And this means they exert a much stronger repulsive force. They literally shove the two hydrogen bonds closer together, squishing that angle down from the ideal 109.5 degrees to the real 104.5 degrees. And that's a pretty good explanation. But it just makes you ask another, deeper question.
Yeah, but why? I mean, just saying they're pushier isn't really a satisfying answer, is it? What is it, fundamentally, about these lone pair orbitals that gives them all this extra oomph? To get to the bottom of that, we have to go one level deeper and look at the very nature of the orbitals themselves.
And this, right here, is where the real story is. It's not just about some vague repulsion. It's about the fundamental character of the orbitals these electrons live in. It's a tale of two different kinds of orbital flavor, s character and p character.
Okay, so remember how we said sp3 orbitals are a mix of one s and three p orbitals? Well, orbital character is just the percentage of each in that final mix. The only thing you need to remember is that s orbitals are spherical, and they're held really close to the atom's positive nucleus. That proximity makes them lower in energy, which is a more stable, more comfortable place for an electron to be.
So in our perfect theoretical molecule, each of those four sp3 orbitals would have the exact same recipe, 25% s character and 75% p character. It's a perfectly even split. And that perfect balance is what leads to the perfect 109.5 degree angle. But, of course, reality has other plans.
And here it is. This is the smoking gun. If you look at the actual orbitals in water that are bonding with hydrogen, the mix isn't 25-75. It's more like 20% S character and 80% P character. The recipe is different. The S character, that nice stable stuff, has gone down, and the P character has gone up.
So, the crucial point is this. The deep underlying reason for that smaller angle is that the bonds themselves have more p character than the ideal. And here's the cool part. Pure p orbitals are naturally oriented at 90 degrees to each other. So the more p character you mix into a bond, the more you pull that bond's angle towards 90 degrees. But what decides how this mix gets divvied up in the first place?
And at last, we arrive at the beautiful, elegant principle that ties this whole thing together. This isn't just happening randomly, it's all governed by a fundamental chemical principle called Bent's rule. This is the master key that unlocks the entire mystery.
And here's the rule itself. Now, it sounds a little academic, I know. But what it really means is pretty simple. That valuable, low-energy sick character likes to be in one of two places. It either stays home in the lone pairs, or it goes into bonds that are pointing toward atoms that don't pull on electrons very strongly. Basically, the oxygen atom is selfish with its good stuff.
And this table just lays out the logic perfectly. Look, the lone pairs, they're not bonded to anything, so the oxygen atom lets them hoard all that good S character. More S character makes them rounder, more volumetric, and yes, more repulsive. So to balance the books, the orbitals that have to bond with hydrogen get shafted. They get less S character and are forced to take on more P character. And what did we just learn? More P character means a smaller angle closer to 90 degrees.
So, let's just step back and put it all together. That seemingly tiny 5-degree difference isn't an accident or a fluke. It's a direct, predictable consequence of a fundamental rule about how atoms prefer to arrange their electrons. And that final shape, it's literally everything. It's why ice floats, it's why water is such an amazing solvent, it's why life as we know it can even exist. And there you have it. The case is officially solved. It's this beautiful, logical chain of events. Bent's rule starts the whole thing by deciding who gets the good C character. The lone pairs win, getting puffier and pushier. That forces the bonding orbitals to take on more P character, which naturally pulls those bonds into that tighter 104.5-degree angle we see in reality. It all fits perfectly.
You know, the story of water's angle is such a perfect example of how asking a really simple question can lead you to these deep, fundamental truths about the universe. It really makes you wonder, doesn't it? What other elegant, invisible rules like this one are out there, quietly shaping the very fabric of our world? Thanks for joining me.